Okay, y'all, new unit. So unit 4 is probability, and we're actually going to break this into two test sections. So we'll have part A and part B, or part 1 and part 2. So probability is tested between 10 and 20% of the AP stats test. So 10%, not much, but if it's a year when they're tested at the 20% range, that could be significant. So we're going to spend, like I said, 2 test cycles on this unit. Here are the AP Classroom videos that can support this if you need more help. Okay, so probability, where do we see this in the real world? So these probability, this stuff is all stuff that's governed by chance. And so we see this in the real world, like everyday life. This could be in weather, this can be in traffic patterns. So what's the probability you're going to get to school on time? Obviously in games all the time, we see this with the lottery. So in class, we did the whole thing with Plinko, so we see that with gambling. World events, a lot of times we see this in election polls. I don't know how to spell that. Life expectancy, like how long do we think that we're going to live? And even inherited traits. So a lot of times we see this with biology. So what is the chance? And that's what this is. So what really is probability? So probability are outcomes governed by chance. So think everything that we've done the past few units, we've talked about randomization, random assignment, random selection. So everything is by chance. But here's the key, many repetitions. So after many repetitions, a pattern emerges. And so what happens is we use stats to help understand these patterns and do predictions. So as always, we have this inference or this prediction. So a little bit of vocabulary here. So our sample space. So sample space are going to be all of the possible outcomes. And we don't really want to do this, but a lot of times, you know, we can list all of those outcomes to see what that looks like. We can do this in a tree diagram. We can do this a lot of different ways, but the sample space means if we list all of those outcomes, then we would have a visual representation of what that looks like. The event is a specific desired outcome. Or a set of outcomes. So our notation is going to be probability of something occurring, so probability of event A. So that's what this nomenclature means. This would be probability of event A. And think of this kind of, if you look at just a standard math class, when we say f of x, we're thinking f when x equals a specific number, right? So what we're saying here is the probability of event A happening, whatever that event is, which we go up here. Okay? So range of probabilities. So this is really, so when should be when. So the probability of an event, so the range of probability, so the probability of an event is always between 0 and 1. So we're going to have fraction or percentages here as we do this, and 100% would be that the probability happens, so it's guaranteed, and a probability of 0 would be that it's never going to happen. So of course, as we get lower in our numbers, the probability would be unlikely to very likely. So sum of probabilities. So obviously, sum we're going to add. So this would be the probability of the entire or the whole sample space. So what we would do is we would add up all of the different probabilities and all of the different individuals' probabilities are going to always equal 1. If we add all of those up, the probability of the whole sample space is going to equal 1. Okay, so we probably won't get to this in class, so we're going to come down here. So theoretical and experimental probability. So here we go. Theoretical probability is what should happen in the given sample space, right? So this is the expectation. So this is what we think is going to happen. And so what really this looks like is the number of desired outcomes over our total number of outcomes. And then we have this empirical probability. And the empirical probability, this right here is just the reality. You know, this is maybe what we expect. This would be our theoretical, but in reality, this is really kind of what we're getting. So our experimental, our empirical is going to be when we perform a simulation or we perform an experiment, and it gives us what really happens in the trial. So this would be the number of successes or the number of positive outcomes that you want over the number of trials. And as we do simulations, this number of trials is going to increase and increase. So obviously, what we expect, right, theoretical, and what we actually get are not always going to be the case, and that's what we want to look at. However, what we know is that we have this law of large numbers. And I know that sounds like something that I just made up, but that's really something. The law of large numbers states that the simulated, so our empirical probability, tends to get closer to the theoretical probability as we have more trials. So to me, this just kind of makes sense. If we took a survey of 22 people in the class and we got a result versus taking a survey of 22,000 people, we're probably going to get closer to our theoretical probability as our numbers, so law of large numbers, increase in our simulation. So bottom line here is more data equals more, or I guess I should say closer to the theoretical. All right, so let me flip this over. So here's what we have. So we have here a probability of 0, a probability of 0.5, and a probability of 1. And so what we have here is when we have a probability of 0, then the event will not occur. And, oh my gosh, I cannot spell today. Will not occur, O-C-C-U-R, that doesn't look right, ever. So this event will never occur is what it's saying. When I have a probability that's 0.5, I have here that the event is equally likely to occur or not occur. So 50%, we say it's equally likely to occur or not occur. When we have a probability of 1, we say that the event will occur 100% of the time. Now, this is the part where we really are going to see the data most often. So it's important that we have our words here correct. So if we see something between 0 and 0.5%, we're going to say that the event is less likely to occur. So event is less likely. So then the opposite of that is we would say the event is likely to occur. So less likely over here and likely when we're in that upper half of our probability. So probability can be written in fractions, in decimals, and percentages. So normally in class and normally on the AP test, what you're going to see is the probabilities are going to be decimals rounded to 3 decimal places. Now this part right here, this is normally what we're going to do, probabilities, 3 decimal places. This 3 decimal places is not AP specific. I would tell you that's a good rule of thumb, but what you'll see is that it's not College Board specific, and so just don't round it. Just don't round it too much. That's the big problem. Okay, so let's practice this a little bit, and then we're going to move on. So, example 1: a bag contains 10 marbles, 2 black, 3 blue, 1 red, 4 white. What is the probability you will pull out a white marble? So, what I have here is the probability that I am going to pull out a white marble. So this is my event right here. This is what I want. I want the white marble. So if we go back to our formula, what I have here is the probability that I'm going to get white over the total number of outcomes. So what I want, actually, I don't want to say probability. This is just white over the total number of outcomes or total number of options that I have. Well, it tells me here I have 4 white marbles out of 10 total marbles. So this would be a probability of 0.4. Now, obviously, I can't round that because that's a rational number here. So it's easy. Okay. What is the probability you will pull out a blue marble? Well, the probability that I'm going to get a blue marble would be 3 out of 10. I have 3 blue marbles in the bucket. So that would be 0.3. All right. So if we look at this in a spinner, so we see spinners, we see things like marbles, dice, cards. Those are all things that we see often when we're dealing with probability problems. So in the spinner below, each wedge is an equal area. What is the probability that the spinner will land on a red wedge? So probability that I'm going to have a red wedge. Now you notice up here I just do W for white or B for blue. Now this was actually not smart of me because B could have also been black. So I really probably should have done B for blue in this case. So probability that I'm going to land on a red wedge. So I have 2 red wedges over 4, 8 total. So this is 1/4, which is 0.25. Okay. Probability that we land on a yellow. So probability that I land on a yellow is going to be 3 over 8, and that is 0.375. All right, super simple when we're dealing with just standard probability like this. Okay, so now let's start adding to it. So probability of a complement. So a complement is the opposite of what we think. So probability that an event does not happen. And so what that looks like is this the probability of 1, because we know that this is 100%, or 1 is the total outcome, minus the probability that it does occur. So what we have is we have this notation, and so the notation for not A, so if I have the probability that A does not happen, so A does not occur, I would say the probability of A prime, or I can say the probability of A with a little c up here. And this is used more often than A prime. So don't get this confused with anything that you've done in other math classes. This just means the opposite, or does not occur. So, and actually here we would say that the complement, because really in this case normally we say if the probability of something occurs, so this would be the probability that it does not occur. And so what this would look like, so the way we would write this is the probability that A does not occur would be 1 minus the probability that A does occur. And the reason why we have this is because sometimes it's easy to compute the complement of an event rather than the event itself. So, for example, up here, it's easy to look at this and say, what is the probability that red doesn't occur? In fact, let me just do that right here. If we use the same spinner and I say the probability that red does not occur, so the complement of red, well, I already have this. So this is going to be 1 minus 0.25, so this would be 0.75. Now, this was perfect because I already had the data up here. You know, it's not difficult on this one. I could have counted it up and it wouldn't have been a big deal. But if you've already got the data, if you want to know the opposite or the complement of something and you've already got the data, you're just going to subtract it. So, doesn't make it bad. All right, let's keep going. So, we talked a little bit about complements. Now we're going to talk about sample space. So, sample space is something that you will not very rarely have to do, but just because it's tedious and time consuming. So this example says a coin is flipped 3 times and the result of each flip noted. So if a coin is flipped 3 times, I have 2 options. I can get heads or I can get tails. So draw the sample space for this event. So it actually wants me to list out my events. So I could have had heads, 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 or heads, heads, tails, or heads, tails, heads, or heads, tails, tails, right? So if the first one was heads, I could have gotten heads or tails for the second one. So now I'm going to say, all right, so if the first one was tails, 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 or tails, heads, heads, or tails, heads, tails, or tails, tails, heads. And that would be all of my options. So here what this says is I have 8 outcomes. So 8 possibilities in my sample space. So over here it says, what is the probability a series of 3 flips will produce exactly 1 head? So if I want exactly 1 head, I have this option right here, which is exactly 1 head, and this one, and this one. So I would have 3 out of 8 possibilities that I would get exactly 1 head. And 3 out of 8 is 0.375. Okay? So the second question says, what is the probability this series of 3 flips will produce at least 1 head? Well, if it's at least 1 head, I have at least 1 here, and here, and here, and here. So the only one that doesn't give me at least 1 head is this one. All right? So if I think about that, I can think about the complement in this one. So if I want to know the probability of, so I'm going to put here the complement. So probability of at least 1 head is going to be 1 minus the probability of no heads. Well, if the probability of no heads, I only have 1 of them, so this would be 1 minus 1/8. So 1 minus 1/8 would give me 7/8. And that is, let's see, 0.875, I think. Hold on. That's my calculator. .875. All right. Now, this one, you could have just as easily done this same thing, but this is just another way to show you how you could do a complement, right? So, remember, probability answers the question, what would happen if I did this many, many times? That's what this is asking. What would happen if I did this many, many times? And so we have this myth of the law of averages. So let's talk about this for just a second so that you don't get jammed up on this. The idea of probability is that randomness is predictable in the long run. So probability does not allow us, this is important, does not allow us to make short-term predictions. This is why we need many trials. So probability tells us random behavior evens out in the long run. Future outcomes are not affected by past behavior. So this is important because just because we got the results of, well, in this case, it's these are all of the probability, but if we were to flip a coin, one outcome or one trial is not going to give us the probability for many trials and a future outcome. So probability does not tell us that it evens out in the short run. If you flipped a coin 10 times and it was heads every time, it will be more likely that you get to flip a tail next. This is the myth that's the law of averages. Just because you flip a coin 10 times and it was heads every time, it is not more likely that you'll get a tail on the next flip. All right, so be careful with that. Don't assume, okay, well, I've got it 10 times, next time it's going to be a false, or it's going to be a tail. All right, so you will often see probability in frequency tables. And so what this says is we've used frequency tables in almost every unit that we've had so far. And when we discuss two categorical data, we have something on the top and something on the bottom. So this is when we did our scatter plots. And we are going to use these to interpret probability. So what this says is a group of 50 high school students were interviewed and asked what their favorite leisure activity is. The results are in the table below. Use the table to find and interpret the following probabilities. Okay? So, this first one, of all the individuals surveyed, so this is key here, of all the individuals surveyed, well, we surveyed 50 individuals. What is the probability of picking a male whose favorite leisure activity is dance? So, we want to pick a male whose favorite leisure activity is dance. So we would have 2 out of 50. So 2 out of 50 is 1 out of 25, and 1 out of 25 is going to be 0.04. All right, this next one says, of all the individuals surveyed, so again, of all the individuals surveyed, what is the probability of picking a person whose favorite leisure activity is reading? So it doesn't signify male or male, it just says picking a person whose favorite leisure activity is reading. So reading, here, I'm going to use a marginal number, I'm going to use 16. So I would have 16 over 50, and I don't know that one, 0.32. All right, so here, of all the individuals surveyed, what is the probability of picking someone who does not consider dance their favorite leisure activity? So what I'm going to do here is I'm going to do a complement. I don't have to do a complement, but I'm going to do it this time because this tells me I know 18 people prefer dance. So I would have the probability that it is not dance. So the complement of dance. And this is going to be 1 minus the probability that they do like dance. So if this is all individuals surveyed, I would have 1 minus 18 over 50. Total number who like dance over the total amount here. So what I have is 1 minus 18 over 50. Which is 16 over 25, and if I want to convert this to a decimal, I would have 0.64. Now, I did this pretty quick in my calculator because I'm assuming that you can do this, but I just did my fraction, 1 minus this, and then if I want to report this as a decimal, you go under math, you go down here to turn your answer into a decimal, which is the second option right here, and that's where I got 0.64. So I can do this super quick in my calculator without having to do a bunch of different keystrokes. I can do this quickly here. Okay. This one says, of all of the females surveyed, what is the probability of choosing a female who likes reading? So of all the females surveyed. Well, this time what I have is, and I'm going to start introducing this just because it's going to make it easier, I think, in the long term. Of all the females surveyed, what is the probability of choosing a female who likes reading? So what I want is I want the probability of, let me just write this down. The probability that they like reading given that they are a female. So in words, they like or choose reading. This line that I have right here is given. This is what I'm going to say is given. They are female. So here's what I have. So probability that they like reading is going to be 8. That they are a female is going to be 30. So probability that they like reading right here, given that they are female. So this is out of 30. This is not out of 50 anymore. All these others said all of the individuals. This just says all of the female individuals. And so 8 out of 30 is 0.267. Okay, so simulations, we already talked about that. So probability is great, we can get an answer, but for us to really get that closer to our theoretical, we want to run a simulation, right? So a simulation imitates chance behavior based on a model that accurately reflects the situation. So this is called a simulation. We want to model something so that we get the results that can be repeated. They're usually done with a table of random digits, your calculator, computer software. Basically, what this simulation is it's like an experiment without doing it. All right, so let me show you what this looks like. You will very likely have to do a simulation or show steps of a simulation at least on a free response question. So what we have here are these different categories. And my categories, we're going to state, plan, do, and then conclude. All right, so think, you know, what we're doing with a scientific experiment right here. What is the probability that a student gets 6 out of 6 questions correct on a true-false quiz when written in Greek? And we're going to assume that the exam taker does not know any Greek. Should the instructor be concerned about cheating? Perform a simulation using the 4-step process to answer this question. So what happens is you're given this random question, 6 out of 6, true, false. It's written in a language you can't assume, but you get all 6 of them correct. So state, identify what you're going to be answering. So the question here is it possible to guess on a true-false quiz and get 6 out of 6 questions correct? Now, it doesn't necessarily state that up here in my question, so we're going to restate this. What is the probability they get 6 out of 6 and they can't understand and they can't read the questions? So this is what we're looking for. All right, so the plan part. Describe the tool you will be using to conduct the simulation. Be clear about what values you are assigning to the outcomes, what you're doing each time you perform the trial, and what you are recording. So this is the tool that you're going to use. So the tool could be, you're going to flip a coin. You're going to use a random number generator. You're going to use a spinner. You're going to roll a dice. Just whatever the tool is. That's what we're talking about here. That's the tool. So Here's what I would say on this. So remember, my plan is describe, and you need to be able to describe this so that whoever's reading it can run your plan. Okay? So when guessing on a true-false quiz, we would expect the student to get 50% of the questions correct. You have true, you have false. It's like flipping a coin. True, false. Okay? So we could do this, flipping a coin and saying if we have heads, then it's correct, and if we have tails, it's incorrect. But most often, y'all like to use random number generators, so I'm going to show this from a random number generator. So I would say, using a random number generator, a 1 is getting the question correct, and a 0 is getting incorrect. Randomly generate 6 numbers of 0 or 1. Important right here, allowing repetition. In fact, I'm going to underline this. Allowing repetition, and document responses as true or false. I'm totally out of space, but I'm not done. Okay? This is one trial. So when you do this, you're only getting one trial. You're running this experiment. You're randomly generating 6 numbers of 0, 1, allowing repetition, document the responses as true, false, or you can say as 0 and 1. And this is one trial. So now what we want to see is, I'm going to come down here. Hold on, I'm going to come down here so I can finish this because we're missing the most important part of this. Repeat this process for, I don't know, let's just say 50 trials. Now, 50 is much bigger than 1, but sometimes this is given. If it's not given, then I would pick this for a number that's big enough for you to actually get statistical data. So 50 would be good. 100 would be even better. Okay? So if we do this, now we have the do part, record the simulation data, summarize the data that you have in your trial. So here's what I have. So I'm going to have questions correct, and then over here I'm going to have the number of trials. Okay, so I'm going to go in here, and remember I go math, I'm going to go over here to probability, and I'm going to go down to my random number generator, and my lower number is 0 and my upper number is 1, and I want to run 6 numbers. So this is what we said up here. We're going to run this between 0 and 1. I'm going to generate 6 numbers. And so questions correct could be 0, 1, 2, 3, 4, 5, 6. These are my options. Okay, so if I run this, I'm going to count my numbers here, and I have two numbers correct. Questions number correct. So I have, let me change my color here so it's easier to see. Only two, so 2 questions correct. So I'm going to run this again. And this time, 1, 2, 3, 4, 5. And then I'm going to run again. Wow, check that out. I have the same numbers again. That doesn't even, what's the probability of that right there? So this time I have 1, 2, 3, 4. I have 4 again. 4 again. 1 question correct this time. 2. 3. That's crazy. We would expect 3, 50%, and that's the first time I've gotten that. So 2, 3. So let me see how many I have. 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to do 20 instead of 50, just to save time. So this would be 5, 3, 3, 4. Wow, look at that. That's crazy. This is not what I expected. 2, 5, 10, 2 more. And 3. Okay, so here's what I have. So what I see is the probability of all of these different questions here, but this is crazy. What do I see down here? So 6 questions correct. When I ran that simulation, I got none. So my conclusion, after we've got the data, we want to answer the question that you asked in your state. Comment on how the results were expected or if they are surprising to you. So I would say, after conducting a 20 trial simulation, we see no trials with all 6 questions correct. We should be suspicious of cheating. Now, here I'm going to say 6 questions correct is statistically significant. We saw we had no trials down here with 6, so we would say this is statistically significant. And a rule of thumb, we're going to get to this a little bit later in the chapter, so a rule of thumb would be that we would say this is going to be less than 5%. So if it's a less than 5% chance, we would say that this is statistically significant. And we'll come back to that. You'll see that again. Okay? Let's see. We are really pushing time on this. So what I'm going to do is I'm going to start another video for these example problems. Maybe try these on your own, and then you can come back and look at the video.